Spherical coordinates completely eliminate x, y, and z, and instead talk about rho, theta, and phi. So these are the Greek letters we're going to use for spherical coordinates. We have rho, theta, that one's familiar, and then phi. Now something that's a little bit frustrating is that spherical coordinates don't have one convention. There are a couple of different conventions, and the only way to really know what's going on is to look at how they define theta and how they define phi. There's theta, this is our polar angle. That's the one we've been familiar with all along. But then this new one, phi, it's an azimuthal angle. So azimuthal is A-Z-I-M-U-T-H-A-L. So we have two angles. Sometimes they're written in this order, polar angle, then azimuthal angle. Sometimes they're written out of order to where the polar angle comes last, the azimuthal angle is in the middle, and sometimes you'll see textbooks and notes where they swap the names. They'll call theta the azimuthal angle and they'll call phi the polar angle. So it can be really frustrating, but as long as you know which one is the polar angle and which one is not, you'll be okay. So to plot things in spherical coordinates, you first start by setting a radius, but this time it's not a radius that's stuck in the xy plane like r from polar coordinates. This radius comes from the origin and it goes all the way directly out to the point. So this is the diagonal radius, or the radius of, say, a sphere. Theta is the polar angle, so that is the angle that rotates in the xy plane, still going between 0 and 2 pi. And then phi, this new azimuthal angle, it starts on the z-axis and it drops down. So phi at pi over 2 would be stuck in the xy plane. Phi at pi would be pointing completely down, negative z-axis. Phi at 3 pi over 2, that would look like the negative y-axis, for example. But since we already have that covered with phi at 2 pi, we've decided, well, not we, but conventionally, the azimuthal angle only goes from 0, aligning with the positive z-axis, down to pi, which is exactly opposite of the positive z-axis. So let's make that little note here. Theta goes from 0 to 2 pi. Phi, however, starts at 0, stops at pi. And that's just because it's redundant to let phi spin all the way around. All right, because we don't quite recognize things written in terms of spherical coordinates, we will want to translate back and forth between spherical and rectangular. You'll notice that there's a lot of similarities between the cylindrical to rectangular equations, with one difference. There's no r in here, so instead of x being r cosine theta, it's now rho sine theta. And that's because we're able to come up with an expression that replaces r, which is rho sine theta. For sake of time, I'm not going to discuss where that comes from here, but if you're interested, it is in our textbook, and I'd be more than happy to talk to you about it in like an office hour. But for now, let's just practice doing some of our conversions. So if we start with a spherical point, then we can already tell that rho is 8, theta is pi over 3, and phi is pi over 6. And once we identify these, we can plug them into our conversion equations to find x. So x would become 8 sine pi over 6 cosine pi over 3. Y would become 8 sine pi over 6 sine pi over 3. and then z would become 8 cosine pi over 6. And we can type each one of those into our calculator to find what they're equal to. So with my calculator, I found x is equal to 2, y is equal to 2 root 3, z is equal to 4 root 3. So the point that in spherical was 8 pi over 3, pi over 6 becomes 2, 2 root 3, 4 root 3. Taking a look at our next example here, we see rho is -2, theta is -5 pi over 6, phi is pi over 6. Now, conventionally, we don't use negative angles for theta, and we don't use negative values for rho. But if we're just doing conversions with these equations, technically it's fine. So if we wanted to do that, we could figure out that x is -2 sine pi over 6 cosine -5 pi over 6, and our calculator can handle that. Y is -2 sine pi over 6 sine -5 pi over 6. And last, z would be -2 cosine pi over 6. And so we type those into our calculator and we can find the equivalent x, y, z. Now because we are more comfortable with rectangular coordinates, we'll often translate spherical and cylindrical into rectangular so that we can picture what the surface is or what the equation is. But also, sometimes we need to convert our rectangular equations and points into spherical and cylindrical because integrating in those coordinate systems is far easier. So let's practice taking a rectangular point and converting it into spherical and into cylindrical. So to convert to spherical, we'll use these equations. Looking at the rectangular point, we can identify x is -1, y is +1, and root 6 is z. So we can find rho by plugging each of those in. So we get 1 plus 6, or 8. So rho is equal to 8. Sorry, rho squared is equal to 8, which means rho is equal to plus or minus root 8. We're going to keep the positive version because that's the ideal way to describe the radius for a a sphere. Next we'll find theta by using tangent theta equals y over x. So that means theta is inverse tangent of y, which is 1, over x, which is -1. And we have to remember which quadrant this would put us in. So if theta is in the polar plane, x is negative, y is positive, that's like quadrant 2. So our angle needs to be between 0 and pi. Actually, not between 0 and pi, it needs to be between pi over 2 and pi to be in the appropriate quadrant where x is negative, y is positive. So whatever angle comes out from our calculator of tangent inverse -1, we need to make sure that we get the appropriate version or coterminal angle or corresponding angle that fits in our range. So calculator spit out for me -0.79, but that is in quadrant, I think 4. So to fix that, we can add 2 pi to it. That's at 5.4. Oh, sorry, that doesn't fix that. Adding 2 pi to it just gives me a coterminal angle that's positive. I want the other solution. So remember that tangent will have 2 solutions, one that fits in quadrant 2, one that fits in quadrant 4. Tangent inverse gave us this one. So if we add pi to it, we will find the one we want. So we're going to add pi to -0.79 to find 2.36 approximately. for theta. And then we need to find phi. So phi would then be cosine inverse of z, which is root 6, over rho, which we found to be root 8. So we go to our calculator, cosine inverse of root 6 over root 8. And I get 0.52 approximately. Now the good news about phi is that since it's defined by the cosine inverse function, we know that we don't have to deal with the same problems that we do with theta as far as making sure that we have the right solution for tangent inverse. And that's because conventionally we decided phi should be between 0 and pi, and cosine inverse is defined on that same range. So we don't have to worry about the calculator spitting out the wrong angle and being in the wrong quadrant. Cosine inverse will be piece cake there. All right, now let's take that rectangular point and convert it into cylindrical coordinates. So using the x, y, z from the original rectangular point, we'll plug them in to find r squared for starters. So we've got -1 squared plus 1 squared, or we have r squared equals 2, or rather r equals root 2. We'll keep the positive version because we like to use a positive radius. Tangent inverse of y over x, 1 over -1. We already did this one, and we know exactly what happened. We got an angle that was outside of our range, and we added pi to it to find the second quadrant, so we know that that's 2.36. Theta is the same between spherical and cylindrical, so that's good news. And then lastly, for cylindrical, we need to find z, which, well, cylindrical has the same z value as spherical, so we copy over, z is root 6. So we have our 2 points. The rectangular version is -1, 1, root 6. The spherical version is 8, 2.36, 0.52. And the cylindrical version is root 2, 2.36, root 6. With learning this new coordinate system, it might be beneficial to try to visualize what some of the equations might look like. And one of the best bits of news you're going to get all day is that spherical coordinate systems are really elegant at describing spheres, for example. And most of the equations that are overly complex and rectangular and still even a little muddy and cylindrical, they can become very simple in spherical coordinate systems. So let's take a look at, for example, theta equals pi over 3. Well, remember that theta is the same in spherical as it is in cylindrical, and theta equals pi over 3 would give you a plane. So you're not allowed to rotate in the polar plane, but your radius can be as short or as long as you want, and your z value or your rho could be as long as you want. So we would have a plane if we let theta equal a constant. If we let phi equal a constant, like 5 pi over 6, phi, remember, is that azimuthal angle that aligns with the z-axis. So if we let phi drop down to 5 pi over 6, and then we allowed it to rotate, and we allowed rho to be as long as you want, it would make us a cone. Rho, if we let, and pause that for a second, the equations that we've used for cones are not that simple, but now in spherical, a cone can be simplified to just phi equals constant. And think back to rectangular. X equals a constant, that was just a plane. Y equals a constant, that was just a plane. Z equals a constant, that was just a plane. But now in spherical, one of the variables equals to a constant gives you a cone. That's pretty awesome. Next we have rho equals 6. Now rho is like a radius, but for a sphere, not a circle. So rho equals 6 is saying a set of all the points that are exactly 6 units away from the origin. This is a sphere. And then down at the bottom, we have rho equals sine theta, sine phi. Now, this is definitely a function of both theta and phi. And if we wanted to figure out what this surface would look like, we would need to do some substitutions. To translate this into an equation that we recognize in rectangular coordinates, let's first remember how to translate from rectangular to spherical. So or from spherical to rectangular rather, we know that x is rho sine phi cosine theta, y is rho cosine phi, just kidding, sine phi still, and then sine theta, and then z is rho cosine phi. So looking at the row that we have, it looks quite a bit like the equation for y, but the right side is missing rho. So we will fix that. I'm going to take the rho sine theta sine phi, and I'm going to multiply it by rho on both sides. Oops. So now I have rho squared on the left and rho sine phi sine theta on the right, which means we have rho squared equals y. But we're not completely in rectangular coordinates yet. We need to replace the rho squared. Remember that rho squared is equivalent to x squared plus y squared plus z squared. So really we have y equals x squared plus y squared plus z squared. And if you think that's a sphere, well, not yet, because we have y on one side of the equation, x squared, y squared, z squared on the other side. So let's subtract the y over. And then we can do completing by a square on the y terms. So to complete the square, I'll take the coefficient on my linear term. So I have -1. We'll cut that in half. We'll square it. That's what we'll add and subtract. That's going to result in y minus 1/2 plus 1/4. If I move the not plus 1/4, minus 1/4. If I move the 1/4 to the other side of the equal sign, we'll have a positive 1/4, and that's equal to x squared plus y minus 1/2 squared plus z squared. Now take a look at that equation, the rectangular version, and then the spherical version. Spherical looks far more elegant and simple. All right, stay tuned. There's one more video, and that's going to show how to integrate in spherical coordinates. Spoiler alert, you're still just doing regular integration. The hard part is understanding the spherical coordinate system.